Hello! In this video, we're going to prove the following theorem. Suppose f is a function from a to b and g is a function from b to c. If both f and g are onto, then g compose f is also onto. So really, what we're trying to prove here is a conditional statement. That is, if this is true, then this is true. So we're going to start off this proof by assuming that f and g are onto. We want to prove that g compose f is also onto. Okay, so then what does it mean for a function to be onto? Well, let me express what it means for f to be onto. For every b in B, there is an a in A such that B equals f of A. So the way you could look at this is for every element in this set, there is an element in this set that maps onto that element in this set. And that's the idea of what it means for a function to be onto. Similarly, we have G is onto. What that means is for every C in C, there is a B in B such that C equals G of B. In other words, for every element in this set, there is an element in this set that maps onto the element in this set. So we want to prove that G compose F is also onto. So let me write out what it means for G compose F to be onto. So in the same sort of way, this is what it means for G compose F to be onto. Now, notice F is a function from A to B, so we see A to B. G is a function from B to C, so we get B to C. G compose F, if you recall, is a function from A to C in this case. So really we see it goes from A to C. So it makes sense. So this is the statement we're trying to prove. And notice we're trying to prove a statement that involves every element in C. So give me any element in C. Now, because C is an element of C, we see that in the definition of G is onto, we know that this statement is true for every element in C. So really, since C is an element of C, it follows that there is some element B in B such that C equals G of B. We could say, for instance, B naught, right? We can choose some element B naught in B such that C is equal to G of B naught. Okay, so now we have B naught is an element of B. But in the definition of F is onto, we see a statement that holds for every element in B. And because B naught is an element of B, it follows that there is some element A in A such that B naught equals F of A. So, in other words, we can choose some element, say A naught in A, such that B naught equals F of A naught. So now we're going to put this all together. Notice that C is equal to G of B naught. But because B naught equals F of A naught, we could replace the B naught here with F of A naught. So we get G of F of A naught. But if you recall, this is the same thing as G compose F, evaluated at A naught. So what we have here now is that C equals G compose F of A naught, which is exactly what we wanted to show. We wanted to show that there is some element in A such that C equals G compose F of A. In this case, A naught is what makes this work. So we're done. This concludes that G compose F is onto. And we are done. So yeah, that's pretty much the idea of how you would prove something like this. Now, technically you didn't need to write up this stuff that I wrote up here. I just wrote it down so it could be helpful, so you could recall what it means for a function to be onto. So yeah, that's pretty much the idea of how you would prove something like this. So yeah, that's pretty much it for this video.